Okay, so uh, a very good afternoon to everybody watching. And my name is Jacob Antony. I am from Abu Dhabi, which is located in UAE. And today I will be talking and giving a webinar on the topic nuclear physics and about its fundamentals and practical applications. So, nuclear physics involves the comprehension of matter and energy through theoretical knowledge and practical implementations. It focuses on investigating the composition, characteristics, and actions of atomic nuclei, as well as fundamental forces and interactions within these nuclei. So, in short, we use physics everywhere. For example, for all of the sports geeks out there, yesterday was the Olympics basketball finals. And towards the end of the game, we all could see that Stephen Curry, the US point guard, was shooting threes and he was making quite a lot of them. And how is physics related to this? It's because he got the angle at which he has to shoot correct, and he also got the trajectory at which he has to shoot the ball right. So physics is pretty much used everywhere. And today I am just going to be talking about a segment in physics, which is nuclear physics. And nuclear physics is right now a very important developing energy. And what I can say is nuclear physics focuses on investigating the composition, characteristics, and actions of atomic nuclei and the fundamental forces and interactions within the nuclei. So for all the people watching who have quite a few doubts about what I've just said, don't worry, I will be explaining it throughout the live. So this discipline utilizes complex theoretical models, advanced experimental methodologies, and diverse approaches to analyze the configuration and durability of atomic nuclei. So here in the slide, we can see that we are going to discuss two topics in this particular webinar. One is the atomic nuclei study. Nuclear physics focuses on analyzing atomic nuclei, probing their structures, constituents, and interactions. And the second is its implications. So we're going to be talking about the field of nuclear physics and how it is used in medical treatments, how it is used in energy production, and how it is used in radiation therapy. And nuclear physics is also used in different sectors, such as nuclear energy, development of nuclear weapons, advancement in nuclear medicine. It utilizes a magnetic resonance and the production of industrial and agricultural isotopes, application of implantation in material science, and the implementation of radiocarbon dating in archaeological studies. So for all these aspects, nuclear physics is used. So now we're going to be taking a look at the historical milestones in nuclear physics. So in this slide, you can see the key developments that shaped the landscape of nuclear physics and its applications. In 1895, Wilhelm discovers X-rays, marking a pivotal moment in medical imaging and radiation studies. So in 1895 is where the first practical application of nuclear physics appeared. And prior to 1895, there were many models which had been created to study the atomic structure. In 1898, Marie Curie and Pierre Curie discovered radium and polonium, establishing fundamental elements for future research in radioactivity. Marie Curie and Pierre Curie are scientists, and in 1898 they discovered radium and polonium, which is key elements in radioactivity. Then in 1901, Henry discovered the radioactivity in uranium, leading to groundbreaking advancements in understanding atomic structure. So in 1901, the scientist known as Henry Becquerel, he discovered radioactivity in uranium. And this has been a key aspect into learning about nuclear physics further in the future and at present times. So he is the one who discovered radioactivity in uranium, which is used as a base element in nuclear physics. And with the build up on that particular discovery is where we have reached the stage right now. In 1911, Marie Curie wins her second Nobel Prize award for her research, and which again improved or gave a clearer image or idea on nuclear physics. So, also along with this, we have to note that James Chadwick's discovery of neutron in 1932 was a breakthrough, and it also uncovered a neutral particle within the atomic nucleus. And together, all these achievements, there are so many achievements out, and I've listed five of them. they have shaped the understanding of our current nuclear physics situation. And this is just going to be helpful for us to elevate and build on this for the future understanding of nuclear physics. So now we talk about radioactivity. So we're going to be talking about radioactivity and what is radioactivity and how it is used. So it refers to the natural occurring process by which high energy rays and particles released by radioactive sources. These rays and particles come from the center of the atom called the nucleus. This radiation surrounds us and has been a part of our lives ever since the creation of a universe called the Big Bang. So, talking about radioactivity. So, in short, in small words, or to get a better understanding of radioactivity, think of it like this. Okay, some atoms are not stable and they have too much energy inside their nucleus. Okay, so there are some existing atoms which are not stable because they have too much energy within their nucleus, and to become stable they release this extra energy, and this is in the form of radiation. And this activity where the nucleus releases its extra energy is known as radioactivity. Okay, and this also changes the atom into a different element or a different isotope of the same element. And for those of you who do not know what an isotope means, I will be getting into that later into this PowerPoint. So once again, I repeat, radioactivity is a process in nuclear physics where the nucleus of an unstable atom loses energy by emitting radiation. This radiation can also be in the form of particles like alpha particles, beta particles, or gamma particles. I hope this is clear to everybody. So now we are going to be looking at the electromagnetic spectrum. So what is the electromagnetic spectrum? In short, it is a range of all types of electromagnetic radiation. And electromagnetic radiation are waves of energy that travel through space. And they vary in length, they can be very long, they can be very short. And each type of wavelength has its own properties and it has its own use. So if you look at this image, at the end of the spectrum, you have radio waves, which are the longest and are used for things like broadcasting music and news on the radio. And as you move along the spectrum, the waves get shorter. In the middle, we can find the visible light, which is the only part of the spectrum we can see with our eyes. So in the particular diagram, the second diagram, as you can see, visible is there right after light bulb. So in that particular region is the only region where we human beings can actually see. All the other spectrum and all the other waves in that diagram are not visible to us, but we can hear it or we can affect it in some way or the other. And at the other end, we can see very short waves like X-rays or gamma rays, which can be used in medical imaging and cancer treatment. I'm pretty sure all of us have heard about the term X-ray. So basically, the rays which are used in an X-ray compound or a machine is very small, and that is why it's capable to reveal very, very small intricacies and details of our bone and if there are any injuries to us. So in short, the electromagnetic spectrum is like a very big map of all different kinds of light and radiation that exist, from the longest radio waves to the shortest gamma rays. Once again, if you look at the diagram, you can see the longest rays are the ones which are used to transmit radio frequencies. And when we use a radio, for example, we always change the frequency, and when we change the frequency, we always end up changing the broadcast we listen to. That is where these waves are used. And the only colors we can see are Vibgyor, the rainbow colors. And that particular wavelength is the one which is only visible to us. After that, the smaller rays come in the form of X-rays or gamma rays, which are mainly used in machines, which help us to develop a better understanding of ourselves. And now, if we move on to the next slide, we're going to be talking about atoms. So atoms have three particles: protons and neutrons in the nucleus, and electrons are in the orbit around the nucleus. Protons are positively charged and neutrons have no charge, electrons have negative charge. So if we talk about this, most of us know that atoms are the building block, atoms are the smallest unit. Yes, but there is more than that, okay? The atomic nucleus, containing the majority of an atom's mass, is crucial for defining its stability and properties. It comprises of protons, which are positively charged, neutrons, which are neutrally charged, and the nucleus is held together by strong nuclear force, which overcomes the electromagnetic forces between the protons. This delicate balance of attractive and repulsive forces ensure the stability of the nucleus. And nuclei can vary in size, shape, and composition depending on the element. And one thing which we have to note is, despite their complexity, nuclei exhibit remarkable stability, and it serves as the foundation for the behavior of matter at the atomic level and influences various chemical and physical processes. Now, atoms we know. Now, I spoke about atoms, I spoke about protons, neutrons, and electrons. Now, I'm going to talk about two different types of particles which are used in nuclear interactions and decay processes. They are named as mesons and baryons. So mesons are composed of a quark. And for those of you who don't know what a quark is, it is a type of elementary element that forms composite particles called hadrons, the most stable of which are protons and neutrons. They control the strong nuclear force between nucleons present in the nucleus and makes possible the exchange of energy and momentum between particles close to each other. Now, if you talk about baryons, they compose particles consisting of three quarks held together by strong force and hence form the stable building blocks of atomic nuclei. They contribute to the stability and structure of the atomic nuclei. So baryons are the ones which are responsible for the stability and the shape of the nuclei. Now let's talk about two other types of particles, which are quarks and gluons. So I'm going to read out the basic definition. According to the theory of quantum chromodynamics, quarks and gluons are considered the major building blocks of matter. This theory explains the strong force that binds quarks together within particles like protons and neutrons. Quarks come in 6 distinct flavors, namely up, down, charm, strange, top, and bottom. And each flavor carries a fractional electric charge and possesses unique properties, including mass and spin. Gluons, on the other hand, are particles that carry a strong force and facilitate the exchange of color charge between quarks. The characteristics of nuclear matter originate from this confinement of quarks within bound states. So I've been talking about different particles, and in the middle of explaining, I mentioned about strong force, strong nuclear force, weak nuclear force. So what is that? So the interaction between nucleons, one of the particles of the atomic nucleus within the nuclei, rely on three fundamental forces. They are categorized as strong nuclear force, weak nuclear force, and electromagnetic nuclear force. So what is strong nuclear force? It is characterized by its short-range nature and immense strength, which basically means strong nuclear force is very strong, but it is also very short in nature. It can act as the medium that binds protons and neutrons together within the nucleus and overcomes the electrostatic repulsion between positively charged protons. So it acts on positively charged protons. So then what about the weak nuclear charge? Weak nuclear charge is also characterized by its short-range nature, and it is responsible for the processes such as beta decay. And what is beta decay? It is a process where neutron is transformed into a proton, and it also emits a beta particle, and it also emits a neutrino in the process. Now, what is an electromagnetic force? It is the force arising from the interaction between charged particles and influences the stability and behavior of atomic nuclei by exerting electrostatic forces between protons and affecting nuclear reactions and decay processes. Now, we will talk about isotopes. Isotopes are different forms of the same atom of a particular element that have the same number of protons but different number of neutrons. Okay, and all the isotopes have the same atom, have same atomic number, but they differ in mass number. And we will talk about that more clearly in the next slide. So here we can see how to calculate the number of neutrons. So in this slide, I've taken two examples of magnesium and of zinc. So the number of neutrons is the total mass number minus the atomic number. Magnesium, the mass number is 24, whereas for zinc, the mass number is 65. And usually when we write an element, on the top comes the atomic number, on the bottom comes the mass number. So it is simply mass number minus atomic number. And for magnesium, the number of neutrons is 12, whereas for zinc, the number of neutrons is 35. Now you'll be looking at the core principles in nuclear physics, such as radioactivity. And once again, I'm going to recap what isotopes are. So radioactivity is a natural phenomenon where unstable atomic nuclei release energy and subatomic particles. Like I said, when they have too much or a high number of particles within them and they are unstable, to become stable, they release energy, and that is known as radioactivity. And isotopes are elements sharing the same number of protons but different neutron count, leading to varied atomic masses. Now, hydrogen isotopes example. So here we're going to take a look at different examples of hydrogen isotopes. For example, protium, deuterium, tritium, and all of these they have the same atomic number, but they vary in mass number. Now, significance of isotopes. They play a crucial role in nuclear physics, medicine, environmental studies, and various scientific applications. Radioactive decay is understanding the process of radioactive decay is fundamental in the field of geology, archaeology, and radiometric dating. So here we are going to talk about the different types of radioactive decay. So we have three types: alpha decay, beta decay, and gamma decay. So in alpha decay, the emission is of helium nuclei. In beta decay, it is the emission of protons or positrons. And in gamma decay, emission of high energy photons. So now when we talk about the penetration in this slide, penetration refers to how far different types of radiation can travel through materials before they stop. This depends on the type of radiation and the material it's passing through. So like I said, alpha particles have low penetration power. They can be stopped by just a sheet of paper or even the outer layer of our skin. Because they are larger and carry more charge, they lose energy quickly and cannot travel very far. When we look at beta particles, they can go through paper but are stopped by materials like plastic or a few millimeters of glass or aluminum. Since they are smaller and have less charge than alpha particles, they can travel further into materials. Gamma rays, they have the highest penetration power. And why? Because they are a type of electromagnetic radiation, such as X-rays, and can pass through most materials, including the human body. If we wanted to stop gamma rays, we would need something very dense, such as lead and concrete, and we would need several layers of them. So basically, in radioactive decay, penetration tells us how deeply these types of radiation can go through materials. And as a recap, alpha particles go the lowest and gamma particles go the highest. So now we are going to look at half-life and radioactive dating. So in this slide, basically, we are going to talk about half-life and radioactive dating. The accurate measurement of decay rates enables scientists to determine the age of various materials with high precision. Radioactive dating is basically when archaeologists find a particular material or a particular object which dates back into history. They use radioactive dating to approximately find which era or which age that particular element or that particular object was in. Carbon-14 dating is suitable for relatively recent materials, while potassium-40 dating is ideal for much older geological samples. Now, carbon-14 dating is utilized for dating organic materials up to 100,000 years based on the decay of carbon-14 isotopes in samples. If we talk about potassium-40 dating, it is applied in dating rocks up to 4.5 billion years by measuring the decay of potassium-40 isotopes within rock formations. And the definition of half-life is it is the time required for half of the radioactive atoms in a sample to undergo decay, forming a basis for dating methods. So in short language, radioactive dating basically gives you the approximate time or era in which a particular object was we've recovered it from. Now, detecting radioactivity, we're going to be looking at the tools and techniques which are used for radioactivity. The Geiger-Müller tube, it detects ionizing radiation by ionizing gas within a tube, commonly used in radiation monitoring and research. So basically, it is often known as a Geiger counter, and it is a device used to detect and measure radiation. It works by counting conducting tiny particles or rays given off by radioactive materials. And inside the tube, when radiation passes through, it causes a small electric current to flow. The device counts these currents, and the more counts it detects, the more radiation is present. It usually makes a clicking sound or shows the count on a screen, helping scientists to know how much radiation is around. So this is one of the methods. Next, they use a spark counter. In short, a spark counter identifies alpha particles by ionizing air between gauze and filament, crucial for measuring radioactivity in various applications. So basically, this spark counter, it has a metal wire and a metal plate with a small gap between them. And when the radiation hits the device, it ionizes the air in the gap and it makes the air conductive, creating a tiny spark. The spark shows that radiation is present, and it is a visual way of seeing when and where the radiation happens. Last but not the least, we have background radiation. It refers to natural radiation present in the environment without any artificial sources. And it is important to distinguish from radiation due to radioactive substances. Now, it is a natural radiation that is used around us. It comes from a variety of sources. For example, the sun to the earth, and even from some rocks and foods. This radiation is usually at very low temperatures and is normal and harmless. It is called background radiation because it's always there in the background of our environment, whether we realize it or not. Now, we're going to be talking about the binding energy in nuclei. So, what do you mean by binding energy? It is the energy necessary to split a nucleus into individual protons and neutrons, highlighting the strong force holding them together. Example of helium-4 nucleus. Helium-4 nucleus exhibits a binding energy of 28.30 megavolt, showcasing the immense energy required to break it apart. The relevance of E is equal to mc square formula. The formula E is equal to mc square illustrates the conversion of mass into energy, emphasizing the substantial energy released during nuclear processes. And how is this applicable in nuclear physics? It is important in nuclear physics for predicting the stability of an atom, for predicting the decay processes and energy generations in nuclear physics. So, like I said, binding energy is important as it gives us an idea of the stability of an atom, and this is its most important use in nuclear physics. Going on to nuclear reactions, there are two types of nuclear reactions, fission and fusion. There are more, but in this, I will be mainly talking about nuclear fission and fusion. In fission, it involves the splitting of a heavy nucleus into lighter nuclei, and it results in the release of a significant amount of energy. In fusion, it combines light nuclei to form a heavier nucleus, and the amount of energy released is quite substantial. So now I'm going to be talking about the other two types of nuclear reactions, which are radioactive decay. And radioactive decay is basically a process such as alpha decay, beta decay, and gamma decay. They result in the emission of particles and photons from unstable nuclei, leading to the formation of more stable nuclei. This process is known as radioactive decay. Now, coming back to nuclear fission and fusion, like I said, fission is the splitting of heavy nucleus into lighter nuclei, whereas fusion is the opposite. It combines light nuclei to form a heavier nucleus. And in fission, the amount of energy released is more than the amount of energy released in fusion. So now we are going to be talking about chain reactions and nuclear energy. There are two types of chain reactions. One is a normal chain reaction and one is a controlled chain reaction. So a chain reaction in nuclear physics is a process where a single nuclear reaction causes one or more additional reactions to occur. This happens especially during nuclear fission, where it can lead a large atom like uranium to split into smaller atoms, releasing energy and more neutrons. These neutrons can hit other uranium atoms, causing them to split and continue the process. And if this process is left unchecked, it can multiply quickly and it will release a large amount of energy in a very short time. Going on to controlled chain reactions. A controlled chain reaction is when this process is carefully managed so that it doesn't get out of hand. In a controlled chain reaction, the number of reactions is kept steady by using materials, like for example, control rods in a nuclear reactor to absorb some of the neutrons. This control allows the reaction to release energy slowly and steadily, which can be used to generate electricity in a power plant. The difference is a chain reaction may be left unnoticed, and a controlled chain reaction is always controlled using an authorized person or using extra equipments. Now we'll be talking about nuclear weapons, the development and impact. So what we can see here is chain reaction energy release. A runaway chain reaction in nuclear weapons result in a colossal release of energy, leading to devastating consequences. This is how a bomb works, for example. One particular atom in a bomb splits, hits the other particular atoms, and this particular process creates fission. And the amount of energy released is very high. And the first ever atomic bomb development. The United States successfully developed the first atomic bomb in 1945, marking a significant milestone in nuclear weaponry advancement. Now we're going to be talking about nuclear reactors, which are used mainly in energy generation. High energy output. Nuclear reactors provide a significant amount of energy due to efficient heat generation from fission reactions. Low greenhouse emissions. Unlike fossil fuel based power plants, nuclear reactors provide electricity without emitting greenhouse gases, contributing to cleaner energy production. Safer concerns. Safety is a critical aspect due to the risks associated with nuclear reactions, requiring protocols and monitoring to prevent accidents. Radioactive waste management. Managing radioactive waste is essential to prevent environmental contamination and requires specialized disposal methods to ensure long-term safety. High construction costs. Building nuclear reactors involves significant upfront investment due to the complex infrastructure and safety methods required for operation. Now, we're going to be taking a look at nuclear fusion, the future of energy. It is an abundant energy source, which basically means that it promises a nearly limitless energy supply if harnessed correctly and sustainably. Minimal waste production. Fusion provides and produces significantly less radioactive waste compared to fission, reducing long-term environmental impact. Now, nuclear technology can be used in all these different aspects, and I'm going to be talking about them. One second. Okay, so in hydrology, nuclear techniques are used to trace water sources and study groundwater movement to better manage water sources. And in art, nuclear technology helps in the non-destructive analysis of art and artifacts to determine their age and authenticity. Food and agriculture, radiation is used to kill pests and bacteria in food, making it safer to eat and expanding its shelf life, a process known as food irradiation. Mining, nuclear tools are used to analyze the composition of ores and minerals, improving the efficiency of mining operations. Industry, radiation is used for non-destructive testing of materials and welds to ensure structural integrity without damaging the object. For the environment, nuclear techniques such as are employed to monitor pollution, study ecosystems, and manage environmental conservation efforts. Space exploration. Nuclear power sources like radioisotope thermoelectric generators, RTGs, provide energy for spacecraft to operate far from the sun. Cosmology. Nuclear reactions and processes are key to understanding the formation and life cycle of stars, galaxies, and the universe as a whole itself. Now, going on to electricity, nuclear reactors generate electricity by using controlled nuclear fission to produce heat, which drives turbines to create power. If you look at this slide, you might be wondering, okay, why haven't I spoken about medicine? Because here we are going to talk about nuclear physics in medicine, and it has so many different applications, but the three most common ones are medical imaging advancements. Techniques like PET and MRI revolutionize medical imaging by utilizing nuclear and physics principles for detailed and accurate scans. Effective cancer treatment. Radiation therapy based on nuclear physics precisely targets and eliminates cancer cells, offering hope to patients in their fight against cancer. Critical diagnostic tools. Radioisotopes play a crucial role in diagnosing diverse medical conditions, aiding healthcare professionals in accurate disease detection and treatment planning. So, in the end, what I would like to say is that nuclear physics offers profound insights into the fundamental forces of nature, unlocking both immense power and potential for scientific advancement. Its applications range from generating clean energy to advancing medical treatments, while also posing challenges that require responsible management. As we continue to harness nuclear technology, it remains crucial to balance innovation with safety for the benefit of humanity. And with that, we have come to the conclusion of this webinar. I thank each and one of you watching for listening and paying attention to this webinar. I hope you all have a good day and a good week ahead.